Hi everyone, welcome to today's session on understanding uncertainty in data-driven research from probabilistic predictions to decisions. Today we're gonna start with the content and look at what is uncertainty. So first of all, what is uncertainty when you check the dictionary? Uncertainty is a situation in which something is not known or something that is not known or certain. As you can see, the definition is already kind of fuzzy and it's not that precise, and we will see that we have the same problem in machine learning, that it's very difficult to actually precisely define uncertainty in a way that you can later on quantify it as well. First, we're gonna check what we already maybe know about uncertainty in classical statistics. So maybe you guys already had a statistics 101 session where you learned about, for example, p-values, confidence intervals, or statistical tests. Just as the graphic here on the right, you can see confidence intervals. So those are those red or blue lines that you can see. And you can see some of those overlap the true parameter, so this mu in the middle, the blue lines actually contain the true parameter and the other ones not. So in this way, already there is the possibility to represent uncertainty about the true parameter with intervals. In statistics, such measures or values rely on distributional assumptions, and they include the sampling uncertainty. However, the problem is in machine learning, we don't necessarily have such distributional assumptions. So we will look at how we can quantify uncertainty in machine learning. Maybe first another quote on uncertainty from statistics. George Box, a famous statistician, maybe some of you know the Cox-Box transformations, things like that. He said, essentially all models are wrong, but some are useful. And this directly relates to the uncertainty in the models and the uncertainty in the data, because since we have uncertainty, it is everywhere, we cannot have like one true model. However, some of them are useful, as you might already know. Okay, so now we move on to supervised machine learning. In supervised machine learning in general, probably many of you already were in touch with machine learning, otherwise probably you wouldn't be here in this course. But again, just to set the stage, we want to repeat shortly that we have, for example, in classification, where we want to learn the relationship of given input data X and the labels Y, which can be different classes. Here in this example, we have apples, pears, and lemon. Or in a regression example, we actually want to predict or learn numerical values given some input data X. And here our input data X can be basically anything. We can have like tabular values, we can have images, we can have text. Basically, we can represent anything here. And oftentimes, such machine learning outputs look precise. So we get a predicted class, we get a score, we get a probability, ranking, recommendation, and so on. They all seem to be very precise. However, there is oftentimes uncertainty included in there, which can look like that. We can have a lack of confidence in the model's prediction, which is the uncertainty in machine learning. So for example, here in this classification example, we have overlapping points. So we don't really know, does a new point here where the question mark is represent orange class or the blue class. Similarly, uncertainty can be understood as the likelihood of a model's prediction being wrong, which also works in classification. So the uncertainty here in this point could also be like, how likely is it if I predict the orange class that it's actually the blue class? Or here in this regression example, the uncertainty is that we don't really know what the right value to predict is. And we might have more or less uncertainty depending on a number of factors. Okay, why should we care about uncertainty in machine learning? A prediction alone does not indicate how much it can be trusted by itself. So for example, here we can look at the medical example. Imagine we have some X-rays and we want to predict whether a patient has COVID or not. If we just look at the average predictive performance, it can hide unreliable cases. So for example, if we say we have an average performance of 95%, it might seem quite high. However, we might not really know whether we can actually predict, we can actually trust this predictive accuracy. And also we don't necessarily know for which patients is the accuracy higher or lower, because we just get averages. Another example is when the uncertainty in a prediction can reveal limitations in the data and the model. Here I'm bringing you a graphic of a 3D printed turtle, which was made in such a way that the shell of the turtle actually has this interesting shapes on it, and it is made in a way to fool machine learning algorithms. So if you, for example, show this turtle to the Google's model ImageNet, you actually get the prediction that this image shows a rifle, but obviously we as humans see it's a turtle. However, the output should ideally have a high uncertainty, so if we actually are faced with such a turtle like that tries to fool the model, and it shows that there is a high uncertainty, we can employ models like, for example, human in the loop, where we give such uncertain examples to actually humans to check. Also, one thing is that the uncertainty can itself be scientifically informative. So if we, for example, have here this example of multiple opinions, so we have, for example, a questionnaire, hate speech detection, whatever, and we see that there is ambiguity in the cases, or we see that the annotators actually give different labels, and we think that this is not an error or this is not false, but this is actually just representing the plausible different opinions. It might be of interest to actually study this kind of uncertainty in the labels there. Thanks again for watching this session, and see you in the next.